I'm really excited to start these 4 sessions off with a fireside chat with Warner North. And Warner, why don't you come up and join us here?
Pleasure to be here.
So I will, I think Warner really needs no introduction to most of you, but there may be one or two that don't know him, I will say a few words about him. So Warner has his PhD from Stanford, was, I believe, Ron Howard's first teaching assistant in the decision analysis.
1966.
Okay.
I am also a student of Howard Rafus when he came to Stanford to give lectures a few summers before that. I think I am the only person who can claim to be a student of both of these leaders in our field.
And Warner told me yesterday, which I was not aware, that influence diagrams were first developed on a project that he was working on at SRI.
This was work in the intelligence community. We were asked to help evaluate the value of intelligence information in the context of a potential war in a troubled part of the world. We worked with experts in that area of the world to come up with a set of scenarios, 20 binary events that might lead to an outbreak of war in that area. So if you made a decision tree out of that, it's well over 1 million endpoints, 2 to the 20th. So how could we make this manageable? And how could we get the probability judgments on those events in a way where it could be done in a reasonable amount of time with an analyst, let's say half a day? The insight was if we developed a structure on the conditional probabilities of the successor events based on what had happened before, we found that with about 6 levels of conditioning, so 2 to the 6th, not 2 to the 20th, then you could do a reasonable job of making this assessment. So we built on work that had been done earlier in the GE Voyager effort to plan the exploration of Mars, making coalesced trees. This was work that Jim Matheson was involved in. And Al Miller came up with the insight of let's make a map of the conditionality, and we'll call that an influence diagram. And it stuck, and the application was very successful, as judged from decades later, because our analysts did a wonderful job of assessing probabilities where high probability events actually occurred subsequently.
Yeah, I think.
However, that data is still classified top secret.
Okay. So the first paper on influence diagrams is somewhere in the vaults in the Pentagon, but it turns out influence diagrams will be rather relevant to the topic today of causality, as we'll see. So, Warner, you've also, I know, you also founded Decision Focus, one of the powerhouses.
I was one of a group that founded Decision Focus, and we did a lot of work in energy and the environment, especially with the Electric Power Research Institute.
Right, and back when I was a PhD student at Carnegie Mellon, kind of decided to decision analysis seemed like a kind of rather cool area to move into. I went to California and visited you and gave a talk at Decision Focus, and really that was my first chance to speak with a real decision analyst. I was kind of thrilled as a grad student. So, Warner, you've also worked for a long time on the Science Advisory Board of the Environmental Protection Agency.
Yes, that started about 1978. And that was in an era when your PhD advisor and colleague in writing a great book, Granger Morgan, was also heavily involved in applying decision analysis to air pollution health impacts. Deborah Amaral worked on that, several other people in the field.
She came to work at DFI.
For a while, Granger was working with people at Brookhaven National Lab. The idea was how can we bring in more expert judgment? And can we use that as a basis for getting information on the potential health effects to help inform decisions on the regulatory control of these pollutants? And I'm going to come back to that because I think that's an area of great interest to those of you in the energy industry, because in my judgment, we're about to have quite a debate on the future of air quality standards, especially the national ambient air quality standards for ozone and particulate matter.
So hopefully we will come back to that.
So we're going to come back to that.
So,
but first,
yeah.
You wanted to ask me about how did I get interested in causality?
Before we do that, I still have one or two other things to say about you, Warner.
Yeah, oh sure. Let me not skip ahead.
Yes. So in 1997, he won the Frank Ramsey Award for his contributions in decision analysis.
Most recent winner. Max.
So I'm. Thank you. Well, it is an honor to follow in the footsteps of many illustrious people, but especially Warner. And in 1999, you received the prize for the Risk Practitioner Award from the Society of Risk Analysis. I think you were the president of the Society of Risk Analysis for a period. And there's a lot more things here, which I would think we will. But one of the things that is kind of remarkable to me is, after 50 years plus of these achievements in decision analysis, one might think it would be time to move into, rest on your laurels, retire, relax. But instead, he is still wrestling with some of the most interesting and thorny problems in decision analysis, at least as I view it, on this issue of causality. I was kind of stunned to hear you reading this book and writing about it, and so it's an area that I've long been interested in. As some of you might know, I for a while was looking at this intersection of artificial intelligence and decision analysis back in the days when AI really didn't quite work, and but it's a different day now. But trying to convince, I was part of a group that tried to convince the artificial intelligence community that probability Bayesian approach, decision analysis, was really the kinds of representations and approach they should be taking. And working with Judea Pearl, who was kind of a leading light in that fight, which I would say after about 10 years, starting in 85 to 95, has been well and truly won. These days, in the AI community, there's no big controversy about at least using probability, although there are different interpretations about what that means, I think, as we might see. So Warner, yes, now I will ask you.
Okay,
thank you, Max. What was it that really caused, why did you become interested in this issue of causality?
Well, it came as an assignment. In my quest for becoming retired, where I am achieving not much success as judged by my wife, I have taken on being area editor for decision sciences in the Society for Risk Analysis, which publishes a journal called Risk Analysis. We have a tradition of doing book reviews. I've done quite a number of them. And our book review editor said, Warner, how would you like to do the new book by our editor-in-chief, Tony Cox, called Causal Analytics? I actually got this book in draft before it went final in publication and spent weeks trying to get through the first 2 chapters, which are, shall we say, designed for the advanced graduate student and how you actually do Bayesian nets and how you use advanced software involving ensembles, random forests, etc. Now, some of you in the room may know that stuff. I would say there is an awful lot to it, and you better be very well grounded in probability and how to manage large data sets. I decided that if I were to do a review of this book, I needed to be able to describe how you get there other than being an advanced graduate student and taking a lot of courses. And I looked at work by leading people in the field and found, aha, Judea Pearl has written a new book called The Book of Why, dealing with causality, and he did it in connection, in partnership with a science writer by the name of Dana McKenzie, who has a history of writing books for the lay audience as opposed to experts in probability. So I told my editor, I think I'd like to do Book of Why in addition to causal analytics. And then I added in Pearl's book from 20 years ago on causality and decided I'd better read that too and try to get a sense of where was Pearl coming from. The big surprise to me in this was how strongly Pearl comes out of the traditional practice of classical statistics and its view of probability. And I will quote from Pearl's Causality book. Probability is a representation of how things work in the world. In other words, it's something you can go out and measure, and it's assumed to be stable. That's entirely different from what I learned from Ron Howard and a variety of writers going back to Laplace, that probability is in the mind. It's a representation of what you know, and it can change very quickly. What's interesting to me about the Book of Why, and I will highly recommend it to all of you who are here.
Can I ask, how many of you have
How many of you have read it?
Okay. Good.
1, 2,
Good.
3. And
I mean,
you may comment, elaborating on what I have to say about what you thought of it and what you learned from it. This is not a textbook on how you learn to do it. It is rather an exploration of the ideas, building a ladder of causality, as Pearl describes it, of how you get to a, I will call it, decision analytic Bayesian approach to dealing with large data sets, where you can make use of what is called in this book Bayesian nets and what I will call influence diagrams as a way of structuring uncertainty.
So, Warner, is there any difference between Bayesian nets and influence
I haven't
diagrams?
figured out if there's any significant difference, but I mean, there may, some of you may be aware of differences. I haven't found them yet.
Well, there's a couple of minor additions that influence diagrams have, which is they have decision nodes and objective nodes.
Pearl points out that in the tradition of classical statistics, there are no decision nodes. There are no variables. The challenge to a statistician is to make sense of a set of observational data describing relationships in the world. Find the patterns, figure out how you can use this data for making estimates and forecasts. But don't perturb it by bringing in decisions and asking what if hypotheticals, what if we did something different, how would this change? Now that's completely different from my training in physics and engineering, where we think about taking the observational data and building a model of how things work, and then asking the question, supposing we did something different. If we want to think about launching a spacecraft toward Mars, supposing we launch at a different time in a different orbit. What does that mean about our probability of getting there successfully?
Absolutely. So, I mean, one of the really interesting things about this book and this discussion, I think, is I'm sure you're all familiar with statisticians telling you correlation doesn't imply causation, and it's quoted in the back of the book. But then statisticians, for the most part, don't ever go on to tell us, well, what is causation then if it isn't correlation? And when you think about it, in decision making, in any practical application of numbers and statistics, like as you say, we want to make some decisions. We want to change the world, and if we don't understand what the causal structure is in the world, how can we do that? So in a certain sense, decision analysts are centrally concerned with causation, even though we may not think about it. Why do you think
we frame
statisticians-
our view of life
Right.
as a series of decisions.
Right.
What can I do, or what can my organization do, or the people that I'm advising who have decisions to make? And finding, even with my background in laboratory physics, understanding errors in collecting data, well, the idea that things would change in a major way, and how do I incorporate new information in probabilities, it was like opening a door. Frankly, I found the work of Ed Janes, who had been exiled from the Stanford Physics Department before I got there. And that's an interesting story. We had a Nobel laureate at Stanford named Felix Bloch. I had taken a course in statistical mechanics taught by another professor off of Bloch's notes. Here's a guy who helped invent quantum mechanics. And the notes were really great. But the probabilities were about essentially what would happen over time in a state space where you have lots of interacting particles, molecules and a gas and the like. And I went in after having some exposure to Bayesian analysis and said, what about this idea of probabilities being revised with new information? And he said, I'm going to throw you out of the office. Probabilities are frequencies. There's no other way to look at it. That's what we do in physics. But you might be interested in the work of this heretic that we got rid of, Ed Janes. I thought, oh, I have an interesting task. And I was able to get a hold of Janes's lectures. Now this became in 2003, after Janes' death, the theory of probability, the logic of science. And it's a great read. And I think the culmination of a lot of scholarship on the Bayesian view of probability. It's also very hard. I have not succeeded in getting any of the graduate students that have worked with me to go all the way through that book. Tony Cox's book is similar in its level of difficulty, which is why I wanted to go to the book of why as an introduction to the ideas.
So it's interesting. As far as I know, among decision analysts, we haven't previously talked much about causality. Why do you think that is?
I'm not sure we've understood what a problem it is for the people that have a background in statistics and probability as generally taught in the United States and maybe elsewhere around the world. The logic building up from the Kolmogorov axioms and how you learn about probability distributions on continuous variables, multivariate applications, the use of regression analysis, tools that have been incorporated in econometrics. These are very widely used. And people really haven't gone into the detail of what are we assuming and how might that introduce real errors in our thinking. I would like to give you a simple example due to Pearl in this book on how we can recognize that we are dealing with a confounder and association as opposed to the causal factors that we would all recognize and want to use. The prediction we want to make is children's reading ability. That's why the dependent variable depending on predictor X. Let's take X as children's shoe size. Get the data, run the regression. You will find that children's shoe size is an excellent predictor of children's reading ability. What's going on here? Just give it a little bit of thought. As children grow up, that is, higher age, their reading ability improves. As children grow up, their feet become bigger, they wear larger shoe sizes. So age is the causal factor that we ought to be using. But maybe if we haven't used all our information beside the data that somebody gave us, we are just getting association. A good predictor, but not consistent with our knowledge base on what's going on here. How do things work? And I would argue that in an awful lot of what's going on in AI and the use of big data sets, we're using predictors that are available and handy and maybe have a history. And maybe that history goes back to we only had one predictor, and so we're doing y as a function of x, where x is a single variable. And what we ought to be looking at is a multiplicity of factors and taking those into account, including nonlinearities and interdependencies among those factors.
So about, I think, maybe 25 years ago, Yuta Perl came to Stanford, gave a seminar on causal networks, and which was attended by Ron Howard and a number of decision analysts. And the discussion became pretty heated, I understand. And I think one of the points of contention was, do those arrows, those influences, do they imply causality? And I think you can tell us that that may be a misconception.
Well, it seems to me causality is sort of in the mind of the beholder with essentially use all the information that you have. I mean, for a long time, we viewed Newton's laws as the causal factor for how our solar system and then how our galaxy and how the universe works. And then along comes Einstein and shows there is a deeper way of thinking about it that gives you better predictions through what has become the general theory of relativity.
Would you call
so,
a
cause in
theory?
one area may get superseded by more knowledge, and we get better causal information.
Right. But I think the argument around influence diagrams is, well, we can just reverse those arrows. We just apply Bayes' rule, and the arrows go in the other direction. So clearly, if one of those directions is causal, then the direction of the arrow has nothing to say about causality.
Well, I will say, I think looking at what, if we think of it in terms of conditionality, that what an influence diagram or a Bayesian net does is give us a map of the conditionality in the sense of we have a sequence of events, and we may not have causality at the level of Newton's laws, but we have very strong observational data that has allowed us, others in our society, back through history to make precise predictions of how things will work. And let's face it, our modern societies build on that. But then we're going into areas of great uncertainty, like the health effects of low levels of air pollution, not the past London smogs, but the kind of thing we're dealing with in the United States at the present. Now, we really ought to be looking at those uncertainties carefully and not making predictions that are convenient because we have a lot of air quality measurements and we have measurements of disease or frequency of death. Somebody collects those mortality statistics from hospitals, And now we put this together and we do a regression of mortality based on ozone levels and fine particulate levels. And we get fits to the data indicating, yes, there's an association. And now we're using regression to extrapolate from data at relatively high levels where we have a strong signal, and think about highly polluted cities in the past where we might be able to find such data. And then we're extrapolating to the present, and our government produces regulatory impact analysis in which we calculate the number of lives that would be saved if we reduce the standard from, say, 75 to 70 or 65. And that's a big number when you multiply the death by the value of a statistical life that the economists calculate. And so in a report such as most recent thing I could find on the net, a draft report on costs and benefits of regulation from the Office of Management and Budget, and they point out that the air quality standards on ozone and fine particulate matter have costs in the single-digit billions of dollars per year, and benefits that are the order of 10 times as great, tens of billions a year. And oh, by the way, the National Academy of Sciences in 2002 recommended looking at uncertainty, especially in those mortality numbers and the benefits of the supposed lives saved.
So Warner, are you saying that maybe those effect is functions are not linear, and so we're not worrying about thresholds? Or are you impugning the claim that there's actually a causal relationship at all?
There's a big debate in the community, which has gone on for some time, on is there a threshold? Are these effects on health and length of life appearing only at high levels and below some level, such as where we have set the present ambient standard,
right,
let's say 70 for ozone? Are there effects of shortening life below that level? And what people say, and I can say this as a journal editor who is in the process in real time of reviewing papers on this subject, that there are many people in the air pollution community who say, we have no evidence establishing such a threshold, so we will assume for our calculation linear through zero. And I will submit that is the default, which is presently in practice, but is now being challenged. And who is the lead in challenging this? It is the author of Causal Analytics, my good friend Tony Cox.
But Warner, I think this issue about threshold is a really interesting and important one, but are you also impugning the claim that there's any causal relationship between air pollution levels and mortality?
Let me give you the example which Tony uses as a teaching aid in causal analytics. Let us take a data set from the South Coast Air Basin that is Greater Los Angeles. And we have, in addition to measurements of fine particulate matter, we have data on temperature and relative humidity. We will summarize that by looking at the maximum temperature in summer months when there are heat waves, and in the winter, the minimum temperature when we get cold spells from air from the Arctic and Canada coming down into LA, where it's very cold there. And we might also look at socioeconomic status. Well, what happens in heat waves? I think it's common knowledge that in many areas, when there is a heat wave, people who live in housing that doesn't have air conditioning tend to die. Often these are poor people and elderly people. In Paris, there was a heat wave that killed tens of thousands a few years back. So it shouldn't surprise us that when we look at mortality with Tmax, we find there's a signal. There's a good correlation. We bring in Tmin, cold spells. People get the flu and colds. More people die then. We look at the difference between wealthy locations and locations where the poor people live. Typically, air pollution is higher in the poor areas compared to the wealthy areas. You put this together in the big data set and ask, what is predicting mortality? Air pollution drops down to a very low level. The other variables are much more important.
Right. So, I mean, you're talking about these studies that are looking at, mortality as a function of, time when you're looking at different temperature levels. But if you aggregate them over years, there's plenty of studies, starting from, Lester Lave's original work and many others, and recent work in China, for example, by Michael Greenstone and so on, where they're looking at mortality as a function of air quality levels aggregated over years. So the temperature differences shouldn't be such an issue.
There's a big difference between the levels of pollution and the types of pollution that are happening in China in the recent past and maybe the present, and what we're dealing with in the United States.
Sure.
And some of it is qualitative differences in terms of what is the pollutant. For example, in China, there was a widespread practice of burning coal in an open pit fireplace with a hole in the ceiling of the dwelling where the fumes from burning the coal would permeate the living space. Well, when you burn relatively low quality coal, you get out benzene and you get out a number of other rather noxious elements, some of which are known human carcinogens. So it shouldn't surprise you that in these dwellings there was an excess of cancer which was quite statistically significant.
Sure. I mean,
now, that's a very different kind of thing than fine particulate matter in the United States now. Now, again, you brought up Lester Lave.
Yes.
20 years ago, I was learning about this and looking at the kinds of regression methods that he was using. And that's exactly why I got interested in the, can we dig below what you get out of using econometric tools and talk about how do we segregate these populations and get in what we know about conditional probability with weather variables and wealth variables so that we can do a better job. If we're thinking about highway risk, driving a certain distance each year, what's your probability of getting into an accident? Are we just going to stop with that? The insurance companies don't. You would want to find out about, is there alcohol use involved? Now add marijuana to that. Age of driver, experience of driver. Is this in a dense urban area, or are we driving on the interstate highway system with low traffic levels, such as I experienced late on a Saturday night, driving from Los Angeles to San Francisco lately? Yeah, that's much safer driving than in downtown San Francisco. So the point is, we know a lot more, and we ought to be getting that data and using it. Now, I thought as I was writing my book review, I'm walking into a hornet's nest with this in whatever I say about Tony Cox's book. Because in the trade literature, I'll use Risk Policy Report with its discussion of how the new chair of CASAC is changing the process, that the subcommittees have been disbanded, et cetera. This is a very political context.
Right. Maybe you can just decode that a bit for some people who don't know this. But Tony Cox has a position as science advisor.
He is the chair of the Clean Air Scientific Advisory Committee, which is chartered under the Clean Air Act to advise the administrator of EPA on the setting of national ambient air quality standards.
And this was after the current administration had essentially dismissed most of the scientists.
This is an appointee of the Trump administration.
Right.
And Tony is characterized in this trade rag and in many other reports as being somebody who is an industry consultant and has been challenging EPA with its cadre of expert professionals that EPA's methods for dealing with causality are out of date and flawed. Now, part of what EPA does is they use criteria owing to an epidemiologist named Bradford Hill as a way of assessing strength of evidence on causality. Both Cox's book and Pearl's book go into some detail on why the Bradford Hill criteria are out of date. Essentially, having more evidence of association doesn't give you causality. Right. That's a nutshell summary of what's going on there.
Right. So do you see this as kind of major progress in terms of our understanding of what causality is?
What I'm recommending to those of you, especially in the energy industry, is you should care about this. This is a set of regulatory practices that have been imposing billion-dollar costs on the economy and especially on your industry. I'm not going to say that this policy is absolutely wrong. I might defend it as we were doing the best we could based on the tools and knowledge we had then. And I can go back to the Lester Lave era and say it was pretty good, but we did some decision analysis in 1975 where we were modeling the source-receptor relationship rather than just looking at epidemiology and asking essentially, if we put stacked gas scrubbers on power plants, what effect is it going to have on the level of sulfates in the Northeast corridor? And well, you got a long distance there. You got some degree of the solution to pollution is dilution.
Right. Very nice.
So maybe you better worry about indoor sources of particulate matter from your fireplace or your frying pan.
Warner, I don't know if you know this, but that model, the decision analysis model that you and I think
Lee Murkoffer
put together, that was implemented as a Fortran program, right?
Well, it was
because I remember taking that as a grad student and re-implementing it in DEMOS, which is the very ancient precursor of our analytical software, as a little exercise.
To be very simple about it, we built a box model. It was a pie slice, not a rectangular box. And then we looked at the detail of the chemistry of the conversion of sulfur dioxide into sulfates. So we got a projection of how much sulfate do you get as a function of distance compared to what was being emitted from the power plant. And then we looked at what was then known about the health effects of these materials.
But given your, the concerns you've expressed about, poor treatment of causality, and I guess you're implying that there really has been some major confusions in people using correlation or regression coefficients as a basis of these policies. Do you really think that if it was done right, or in the future, when it gets done right, the results will be radically different?
Well, what came out of our analysis that I thought was useful was a very high value of information calculation off a simple model.
Right.
And this is trying to deal with the issue of, we have a point estimate of the health effects, and it's big. Bernie Goldstein was the designated health effects expert, and I dragged him kicking and screaming all the way, and to give me a probabilistic description of what we know about the health effects. There was a baseline which had come out of some questionable research, and he said, in my judgment, the health effects could be twice those numbers or as small as 1/10 that. So I put those as the 95% points on a distribution. And that allowed me to calculate that the value of getting better information was very high.
And I mean, since then, there has been an enormous amount of empirical work on these questions, and I mean, even recently, where there's like much more detailed data available. Do you think the uncertainties have been reduced by that?
I think we know a lot more, and I think we've gotten away from our biggest problem is sulfate as a component of fine particulate matter. I mean, you can measure it easily. These materials are soluble. But look at what else is out there. We have carbonaceous materials, we have trace metals, we have wood smoke, particulate matter, which is mainly carbonaceous. Now, what's causing the health effects? We are still making the assumption within EPA that all particulate matter should be viewed as equally toxic. Many people who have been in this field have done this epidemiology repeatedly over long periods of time without getting into the detail of what else is there in the potential data beside measuring air quality at ambient sampling points, which may be tens of miles from where people live and work, and measuring mortality by looking at the data from hospitals on how many people die on a given day.
Right. So, I mean, as I understand Pearl and Tony Cox maybe as well, they are now saying that if you do the analysis right, you actually can identify causality when there are, at least if there are explicit interventions there. Do you think, is that?
I'd like to paraphrase this, and I'm trying to be very careful here. Tony Cox has done one exercise on one limited data set in Southern California and concluded on that data site that you have much more evidence for causality with Tmin and Tmax than you do with fine particulate measurements. I'd love to have that replicated
Tmin and Tmax
across many more cities and a larger time period.
Right.
I won't say it's absolutely right, but I would say it's a direction we need to go.
Right. Can you, for those of us that may not know what Tmin and Tmax are?
This is maximum summertime temperature and minimum wintertime temperature. And you know, when you run these data sets, you find out that in winter months, Tmin is an excellent predictor of elevated mortality. And Tmax in the summertime is an excellent predictor of elevated mortality. Remember, we're looking at a very small signal in noisy data. So air pollution versus mortality, yes, you'll find an association. But are we looking on the right variables? Again, remember shoe size and reading ability. Do we have association? Do we have causation? I'll claim it's a good question. But let me switch to another example. I thought in writing my review, if I just focus on air pollution, this is going to look like a political statement supporting my friend Tony. I don't want to do that. I don't want to go there. So let me pick up something else where we're not talking about shortening life, we're talking about lengthening life. And it's a decision we all make on what do we choose to eat. I happen to like mixed nuts.
Yeah, we actually need to wrap up, I'm afraid.
I'm sorry, what are we? Let me take a minute and finish this. So I can find epidemiology readily available on the net, referenced in my book review, that if you eat mixed nuts, it will on average extend your life. The number is like 2 years. The database is a huge set of numbers from physicians and nurses keeping diaries on what they eat and tracking their health status over a period of decades. Is this association or causation? The investigators say this is association. We won't claim causation. People commenting on this epidemiology say, what could be the confounders here? Is it alcohol? Is it exercise? Is it socioeconomic status? The response is, we checked for alcohol, exercise, and socioeconomic status. Nurses and doctors are affluent people, this is a relatively homogeneous population. We don't think those are confounders. I ask myself, what might be the confounder here? What ought to be measured? Well, do these people eat the same diet? How about other kinds of fat and fiber? Greasy hamburgers and German sausage, or vegetarian? You know, what else goes in their diet beside mixed nuts? Okay, my review goes off to press and finalized. New York Times, AI and diet. The investigator goes off and has an AI profile done on diet, including mixed nuts. The health endpoint being predicted is not longevity, but it is a measure of health, glucose spikes, blood sugar spikes for somebody who's a diabetic. That's very important. That was the case for this reporter. Okay, dig in. What do we find? What's the equivalent of age in that shoe size? It turns out to be bacteria in the gut. Okay, we go looking, we get more data. We're going to find out more about what might be the causal factor.
So, I mean, you're making some very interesting and provocative points here.
That's my intention.
Good. I think you've succeeded there. I think what I'd like to, so the discussion about confounders and causality in a lot of these fields has been, on and off going for quite a while. But I think what I'm wondering if there is some kind of take-home message for us as decision analysts, let's say. Is there something new and important in this work by Tony Cox and Yuta Pearl that we can sort of say, okay, there's something important here, we really need to learn this, and really we have some different tools that we can use based on that?
Well, I will give you my impression and invite the three people who've read the book to give me theirs.
Right.
And that is, I think we in the decision analysis community will learn a lot about those that are not part of our community and how they think by reading the Book of Why and the history that Pearl provides on how people in his community have thought about probability and uncertainty. And the take-home message, I believe, is that if you come out of this tradition that probability describes normal relationships in the world, then you will miss the whole point of those of us who are Bayesians and think in terms of decisions and how probabilities change with new information. We're going to have to bridge a gap here to have an effective dialogue with those people. And for somebody who's been frustrated for years in my limited ability to communicate with others in the scientific community, I think this will be very useful for you. And second of all, if you want to learn how to do it, it's very complicated. Tony Cox's book will be a lot of help to people that are going to try to learn how to do it. And I think of a number of university-based groups that I know that are using Bayesian nets for very advanced analysis. My most recent data on that is from UCLA with a bunch of people from nuclear engineering who are using Bayesian nets for very elaborate analysis. Okay, Cox's book and Pearl's earlier work in its sum total may be very helpful, but this is climbing a very difficult mountain to get there. Now, causality. Let me make a point about AlphaZero. AlphaZero is a computer program that's beaten all the computer programs written to play chess and Go, and the Japanese equivalent of chess, shogi. How does it work? This is also in my review. What it does is it takes just the rules of the game, and then the computer plays itself millions of times, which with modern computers we can do, and it builds up its own learning for how to win at these games. Now, what's causality there? I would say it's very deep learning from experience that the computer can do faster than any human being will do. And out of that, the computer learns what works and becomes very effective. Can we characterize how the computer does it? Not easily, but if we dig, maybe we'll see the patterns and we'll learn something too. And it takes humans to set up these situations where the computer attacks a very complicated situation repetitively and learns how to do it. Games such as chess and Go are well-defined. Other games are ill-defined, and it's a harder problem.
Yeah.
I'm going to conclude by quoting my friend Sebastian Trun, who was the AI guy who won the autonomous vehicle race across the Mojave Desert. He's quoted in the New York Times saying, "Computers are dumb, but they can learn from examples." I've given you a set of examples. I think by working with examples, we can do better in educating those that are not part of our community, and we can also learn how to be effective. I think trying to define precisely what is causal and what is not, that's going to be extremely difficult. Rather think of it as a learning process where we learn to do better instead of not so well.
Thank you so much.